Hello class, this is section 5.2. We're going to be looking at infinite series. And in section 5.1 we looked at sequences, and a sequence is just an infinite ordered set of real numbers. A series is going to be adding terms of a sequence. And so a series, because you're adding terms of an infinite sequence, the series is a sum that has an infinite number of terms in the sum. So capital sigma, that's going to be sum of n equals 1 to infinity, where the n is the indice on terms of a sequence. So a sub n is a sequence. I'm going to add all the terms in a sequence. So notice explicitly it's a1 plus a2 plus a3 plus etc. And the sum goes off forever. Now when we try to find the sum of these infinite series, it's not as straightforward as trying to add a finite number of terms. So how we add a series is we think of the series of just partial sums. So we'll look at what's the sum of the first 5, the first 6, the first 7. And each of those will be a partial sum, and we look at the limit of those partial sums to see if those partial sums converges to a real number. All right, so a series is an infinite sum, and those items in the sum are just terms of a sequence. All right, so here's, again, just reviewing the notation. N equals 1 to k of a sub n. When this is an infinity, this is going to specifically add just k terms. So a1, a2, a3, all the way to ak. This notation will be the kth partial sum. It's the sum of the first k items. So if this indice k was 5, it would add the first 5. If this indice were 10, it would add the first 10. So let's look explicitly at a particular example. And we'll look at an example that actually involves kind of an application here. Suppose that I have oil seeping into a lake, and the first week's 1,000 gallons. The second week it's 500 gallons. The third week is 250, etc. So the fourth week would be 125, and this pattern would continue. So we could look at, the amount of oil in the lake, and we could look at, instead of having the number 1,000, we could call 1 being 1,000, 0.5 being half of 1,000, etc. All right, so we can look at this in equivalent terms, and the terms would be, the sum would be, for the first term would be 1, meaning 1,000. So basically we're making these units a little bit easier. The second partial sum, so adding the first two terms, would be 1 plus a half, right? That's representing 1,000 and 500. Okay, and that's 1 plus 1/2. The first three terms are 1 plus 0.5 plus 0.25. So you'd have this, etc. The sum of the first 4, here they are explicitly written out. The sum of the first 5, again, explicitly listed out. So we're going to see if we can't spot a pattern. So the first term added to itself, first 2 terms added, first 3 terms added, first 4 terms added, first 5 terms added. In general, S sub k would be the first k items added. And if we look at what's going on, it's 1 plus 1/2, and these keep decreasing by a factor of 1/2, 1/4, 1/8, 1/16. Okay. Dot, dot, dot. And so the 10th one would be 1/2 to the 9th power. The 11th one would be 1/2 to the 10th power, etc. And so the sum would be 1 to k, 1/2 to the n minus 1. So where do they get the n minus 1? Well, the first term in the sum is 1/2 to the 0 power. So that's why I want a 0 power here. The second term in the sum is 1/2 to the first power. So when n equals 2, I get a power of 1, and I have a 1/2 added. So this is shorthand notation for this explicit sum here. Okay, I'm adding k items. Here's the compact notation. The sum from 1 to k of 1/2 to the n minus 1. So now if we, write it out like this, and we want to look at the limit as k goes to infinity. So notice here, this is the kth partial sum. So explicitly, I'm only adding a finite number, k of them in fact. And then if the limit exists, then we're looking at the limit as k goes to infinity of this partial sum. So where's k? It's this upper limit on the sum. So here we're going to infinity here. So the limit s of the series, if it exists, is going to be an infinite sum, and it's going to be the limit of this partial sum. Let's look at some of the partial sums to see if we can't just intuitively see a pattern. First one is 1. Add the first 2 together, it's 3/2. Add the first 3 of them, you get 7/4, and etc. Add the first 5 terms, get 31/16. So it looks like, just from intuition, this might be converging to 2. Let's go ahead and look at the graph here. So they just graphed. Here's s sub 1, s sub 2, s sub 3, s sub 4, s sub 5. Notice these partial sums just make up a sequence. Okay. Here we're looking explicitly. If we type this into your calculator, you could easily type in this as a function here, 1/2 to the power of x minus 1. And then in your table on your TI-84, you could type in x equals 5, x equals 10, etc., and get this partial sum here. Okay. And now if you look, the 20th partial sum, meaning adding the first 20, is really close to 2. Okay. So of course we're not going to be just using numerical results to prove something has a limit. Okay. But later on we'll be able to show that this indeed is 2 because this is in fact a geometric series. Okay. But right now we're not going to go through the proof because we have to get to that section where we talk about geometric series. But for now, it looks like, according to just looking at partial sums, that this might be going to 2. All right, so let's get to some definition here as far as the notation that we've been using. An infinite series is an expression of the form n equals 1 to infinity of the sum of the terms of a sequence a sub n. So that's the definition of an infinite series. It literally is a sum of an infinite set of numbers where those numbers form a sequence. And for each positive k, the partial sum, s for sum, s sub k is just simply a finite number of terms added together. It's the first k terms. So s sub k is the sum of, a sub 1 plus all the way through to a sub k. Okay? So infinite series is the sum of an infinite number of terms of a sequence. The partial sum is simply adding the first k items in the series. Now, the infinite series is said to converge if and only if these partial sums converge to a real number. So if the limit of s sub k as k goes to infinity equals some number s, then we can say that the infinite series converges to that number s. All right, now that we've got this definition, let's look at some examples.